guys, welcome to the continuation of tutorial sheet 8, sorry. So we are going to continue from where we ended last time. We did question 1, 2, 3 and 4. So today we'll do question 5, 6 and 7, and in the next video we are going to have to finish tutorial sheet 8 so that we can start solving tutorial sheet 9 since it's already out. So we'll start with question 5, the one you submitted as an assignment. I skimmed through the work that a lot of you did, and it was alright. It was correct, in short. A lot of the papers that I went through had correct answers. So just for the sake of, I'm going to do it quickly, and then we'll go to question 6 and 7. So this is question 5. And the question reads, a uniform 400 Newton boom is supported as shown. So, as shown here, find the tension in the tie rope. So this is the rope that we are finding the tension of, and the forces exerted on the boom by the pin at P. Of course, P is somewhere here. Okay, so that's what we have. Now, we have to find the force, the tension in the rope and the forces here. How do we go about doing that? Since this system is assumed, or the system is in equilibrium, right? Meaning that the forces in the x-axis are equal to the forces in the negative x-axis are equal to the forces in the positive x-axis, the forces in the y-axis in the positive y-axis are equal to the forces in the negative y-axis. Okay, so this will be x, this will be y, so this will be positive and this will be positive, meaning the opposites will be negative. Okay, so now to find, let's start with the forces in the y-axis. Okay, so the summation of forces in the y-axis is going to have to give us a 0. Okay, so in the y-axis we have got 3 forces. We've got this force, which is the weight of the boom. We've got this force which is hanging, and of course this force which is at point P and is in the positive y-axis. Okay, so we've got this force here which is at the center of gravity, and then we have got this. So these two are acting downwards, so meaning that there will be negative, whilst the force here is going to be positive. Right? So we'll have the center of gravity, which is at 400 newtons, negative 2000 newtons plus P should give us 0. Okay, meaning that P will be equal to 400 plus 2000, and that will be 2400 Newton. So this is the force that P is exerting in the y-axis. Okay, now we want to find out the force that is acting with reference to the rope. Mind you, the rope is pulling in the x-axis. Okay, we have got this force which is pushing, and the rope is pulling at this side, meaning that the magnitude of the tension in the rope is equal to the magnitude of this force that is acting at point P. Okay. Now, how do we find this force? To find this force, we are going to use torque. Okay, we're going to use the second condition, which is that the net torque of systems in equilibrium is supposed to be 0. So if the net torque is 0, then that will help us to find the rope, or the force, the tension in the rope. So if we take moments about this point, just here at P, we are going to have this force, so have the torque, with reference to this force here, which is from the center, the torque with reference to the rope, and the torque with reference to the 2000 Newton. Okay, so we have three forces. Now, we know that for torque, we have to use the perpendicular distance. If you look at this, the perpendicular distance of this force is actually the distance, which is this distance from here to here. That is the perpendicular distance, okay? And then if we look at this rope, its perpendicular distance is which distance? Okay, so we're going to have to find the perpendicular distance of this rope, where this rope is positioned. Which one do you think it will be? Okay, as in which one will it be? Then if we look at, oh, I've made a mistake. The perpendicular distance for this force is the distance from here to here. Okay, the perpendicular distance of this force, which is the tension in the rope, is the distance from here to here. Okay, then if we look at the perpendicular distance of this 2000 Newton force, it's going to be, or we can simply just take this distance since it's going to be the same. Okay, so it's going to be the distance from here to here. Okay, that will be perpendicular. So if we draw a line like that, then we'll have this distance. Okay. Okay, so now if I want, sorry, there's a bit of light here. So I'm going to have to be, I'll be working with the force here, since this is a perpendicular distance, so meaning I'm going to have a 40 degrees here. Okay, so I want to be working with this angle here so that it will be easier for me to calculate these distances here. Okay, so like I said, this is the perpendicular distance for this force, this is the perpendicular distance for this force, and then this one here will be the perpendicular distance for this force. So to calculate the torque, we are going to say, of course, this is going to have a clockwise turn if we assume that it is rotating. So we'll have negative L over 2, since it's the center, it's acting at the center of mass, meaning it's at 1 over 2. So multiplied by L, that's negative L over 2, since we've not been given the length of the boom. So negative L over 2 multiplied by, to find this value, we are going to find the sine, to multiply by sine 40, okay? Because we have this value now, we are looking for this value. So this value is going to be the sine of this angle. So we will multiply that by sine 40 plus, we come to this force that's acting at the force that's with the rope, the tension in the rope. So this is going to be that, and then the distance, the perpendicular distance, which is here, is going to be this distance multiplied by the cosine of the angle here. So we'll have 3L over 4 cos 40 multiplied by the tension. Okay, since we've not been given the tension, that's what we are looking for, minus, now if you look at this, this is at L over 4. So the distance from here to here is L over 4. So meaning the complete distance here is L. Okay, so we'll have L multiplied by the perpendicular distance, this perpendicular distance, which is the sine of the angle here, multiplied by this perpendicular distance, multiplied by the force hanging. So we'll have L sine 40 multiplied by 2000 newtons. Here I forgot to multiply this by 400, the force which is acting at the center of mass. Okay, so that's what we have. If we simplify this, we are going to have 0.32 negative multiplied by 400, okay, plus 0.575 t minus 1285 newtons. Okay, we simplify that, meaning that T is going to be equal to 1,285 plus 128.6 divided by 0.575. Okay, that will give us the final answer as 2,460 newtons. Okay, that's the tension in the rope that we have here. Okay, now if the tension in this rope is 2,460 and these two forces are the only forces that we are having in the x-axis, meaning that these two forces are equal but in opposite but have got opposite signs. Okay, so if this is negative, then this will be positive. All right, because it is acting in the positive x-axis, so meaning the other one will be negative. So meaning the force at P is equal to, okay, so the force P will be equal to 2,460 newtons. Okay, now the question has also asked us to find the force that is exerted on the boom by the point at P. So we have at point P, we are having two forces, the force in the x-axis and the force in the y-axis. The force in the y-axis is the one that we had calculated earlier, which was 2,400. Okay, and the force in the x-axis is the one we're just from calculating, which is 2,460. Okay, now we want to find out the resultant of the two forces. Okay, the resultant of the two forces will be, so if you look at the resultant of forces is usually found, we'll have x squared plus y squared. Okay, so that will be equal to 2,400 squared plus 2,460 squared. So that once we square these two, we are going to get the resultant force, which is the force at the resultant, okay? Because we have got it in the x and in the y-axis. So the resultant will be acting at this point, somewhere there. So we'll find the resultant, and using trigonometry, you can also find the angle at which it is acting on the boom. Okay, that's what you're supposed to. So you can just finish that up by finding the resultant of this, which will be the resultant force acting at point P, and then the angle, of course. Since force is a vector quantity, it has both magnitude and direction. So you have the magnitude, and for the direction, you simply have to find the angle, which is obviously going to be tan theta being equal to y over x, and then theta will be equal to tan inverse of y over x, and you're going to get the direction of the force in question. Okay, so that's how you complete the question. Then we go to question number 6. Okay, I'm sorry I do not have a hard copy of the tutorial sheet, so I'm going to be solving directions. You have the question. I'm assuming that you're going to be using your question as you are viewing this, your question paper as you are viewing this. So question 6 read, calculate the magnitude of the force applied to the shoulder that will topple a person of, we are given that mass is equal to 65 kg. Okay, all right, and then we're also given that the height of the person to the shoulders, okay, was 1.5 meters, and the width of the foot was 0.1 meters. That's the information we are given. Okay, so now before we go into solving questions to do with the human body, okay, the center of gravity, when it comes to, like, an example of a boom, the previous question was just from solving, when you've got objects such as this, we usually take their centers as the center of gravity. We take that the force is concentrated at this point, which is the center of gravity, meaning which is usually at the center. Okay. Now, for a human being, the center of gravity, like a normal human being that is standing upright, that is an erect person with arms sideways, okay, not where the person has got their arms spread out, but when the person is just standing with arms on the side, the person's center of gravity is approximately 56% of the person's height. So if this is 100% of the height. If this is 50, meaning the person's center of gravity is slightly over the 50%. If your height is like 2 meters, your center of gravity is less likely going to be at 1 meter. It's going to be slightly over 1 meter. All right. So when a person is stable, an erect person will have their center of mass at about 56% of their height. Okay. Now, if the center of gravity shifts, that comes in when the person has shifted. Okay. Like if this pen is a person and they are stable in this way, if they shift even a little bit, that means their center of gravity has also shifted. Okay. And that might disturb their stability. Okay, so the center of gravity shifts as the person moves or bends. The act of balancing requires maintenance of the center of gravity above the feet. Okay, so the person falls when the center of gravity is displaced beyond the position of the feet. Okay, meaning if the center of gravity of the person is way beyond the position of the feet, the person can fall. All right, now if the body is subjected to an external force, like in the case of the question, you've got a person, okay, I am very bad when it comes to drawing, but I think there's something like this. So if there's a person here and there's an external force that is pushing this person, okay, if the person if the body of this person is subjected to external forces, the chances of or their stability is disturbed, in short, okay, because a person, just like any other object, has got their center of gravity, all right, which acts like I'm from explaining slightly beyond their center. So that force acts downward. If we have got a force that is pushing on the person from any shoulders, it can cause the person to topple. All right. So now we want to find out how much force will make a person who has got a mass of 65 kg, a height to the shoulders of about 1.5 meters, and the width of their feet is 0.1 meters. What force will it take to make this person topple? Okay. So now, if the separation distance between the foot of the person is 0.1 meters, okay, and then the distance from here to here is 1.5 meters. We can calculate the torque, okay, we can calculate the torque that is going to make this person topple, all right. We know that for stable objects, the summation of torques is 0. Okay, so and if that is the case, then let me try to draw a person as an object, just so that, okay, there. So meaning the distance from here to here is 0.1, then we have got 1.5, and then there's a force which is Fa. Okay, now we want to find out this Fa. If this object is in equilibrium, meaning this, of course, we have got the force here, which is acting downwards. This is mg. Okay. If this force is going to make this object topple, meaning the torque with reference to the torque of this force has to be equal to the torque of this force. That way, the person is on the verge of toppling. So now we want to find out this. So using this condition, the condition that the net torque is equal to 0, we can say that the clockwise, this of course is going to be clockwise, if we take the pivot to be here, okay? If we take the pivot to be here, meaning the distance from here to here is 0.1 multiplied by the perpendicular force. So we'll have 0.1 meters multiplied by mg. Okay, that's clockwise. It has to be negative, but I'm just going to use an equal sign so that we'll have both of the torques positive. Okay, so then the other torque that we have is going to be at a perpendicular distance of 1.5 meters multiplied by the force, which we do not know, the one that we want to find out. Okay, so 0.1 multiplied by the mass of the person is 65 kgs multiplied by the acceleration due to gravity, which is 9.8, is going to give us 1.5 meters multiplied by FA. So this results into 63.7 Newton meters equals to FA divided by 1.5 divided by 1.5. So FA will be equal to 42.5 newtons. Okay, so if a force of 42.5 newton is applied on the shoulders of this person, okay, then the person is on the verge of toppling, because this force is going to produce a torque which is going to be equal to this torque, which is as a result of the perpendicular distance of the feet and the weight. So if a 42.5 force is applied, the person is on the verge of toppling. Okay, if the force is increased, the person is going to really fall off. Okay, fall over. Okay, so then we go to part B. Part B asks us to explain why stability of a force against a toppling force is increased by spreading the legs. Okay, now with part B, if you go back to high school, we learned that the stability of an object is increased by reducing the height. Okay, reducing the height, and this is not just with human beings but with every object. If the shorter the object, the more stable it is. Then there's also the issue of base area. Okay, the base area was the area that the object has covered on the surface. Okay, so if this is the surface, all right, if this is the surface and the object is only covering a small area of this surface, meaning that object is not as stable as an object that will cover a greater portion of the same surface. Okay, so the greater the surface that this object is going to cover, the more stable it is. So the same goes on with a human being. When the human being is standing with their feet together, okay, with their feet together, their stability is not as much as the stability will be if the feet are spread apart, because when the feet are spread apart, then they have occupied a greater base area, hence leading to their stability. But with the feet close, like in part A, the stability is not so much. The person is stable, but the person will be more stable if their feet are more apart. If the feet are more apart, then the stability is increased because they have covered a greater base area compared to when the feet were close. Okay, so like how we know that, if you look at question C, question 6C asks us to calculate the force required to topple a person of mass 70 kg. So we are having the same question. The only difference now is that the mass of the person has increased to 70 kgs. Okay, and then we've been told, of course, the height to the shoulders is still 1.5 meters. Then we have the distance between the feet, which has been increased. Okay, this is now 0.9 meters. Okay, now the 0.9 meters is like, okay, we assume these are the legs of the person, so the separation distance is 0.9, so meaning the center of mass is somewhere here. Okay, so the distance from the pivot to the center of mass is not going to be 0.9 but half of 0.9, which is going to be 0.45 meters, right? So the perpendicular distance is going to be equal to 0.45 meters. Okay, so now we want to find out the torque, the force that's going to make this new person topple. We are going to use the same procedure that we had used in part A, where we say that the summation of the torque is going to be equal to 0. Okay, meaning that we are going to have to multiply the 0.45 meters multiplied by the weight of the person, which is 70 by 9.8, and that is going to give us 1.5 meters, which was the perpendicular distance of the force being applied across the shoulder. So multiplied by FA, that's what we have. So if we multiply this, we are going to get FA will give us, so 0.45 multiplied by 70 multiplied by 9.8 is 308.7 divided by 1.5 meters. So FA is now 205.8 newtons. We can approximate that to 206 newtons. Okay, so now if you look at it, there's a very big difference. To topple a person who is standing with their feet close, you don't need a lot of force. They are not so stable. With just a force of 42.5 newtons, you can topple them. Okay, but then although the mass of this person is slightly higher, but if you look at the difference, 206 and 42.5, there's a very huge difference, right? Meaning you're going to need more force to topple a person whose feet are spread apart compared to the person whose feet are closer together. Okay, so this person with the feet 0.9 meters apart is more stable because they have occupied a greater base area compared to the person who is standing with their feet close. Okay, so we go to question number 7. So question number 7 reads, calculate the mass M needed in order to suspend the leg shown. So the leg shown, I can draw, it's not so complicated compared to the person. So we had, there was this. Okay, so there was a mass hanging here, mass M. Then we had a person's foot. The person's foot here. So we had a hip here, and the center of mass of the person was here. Okay, so the mass, I already start reading the question. Calculate the mass M here needed in order to suspend the leg shown. So assume the leg has a mass of 15 kg. So meaning we have 15 multiplied by 9.8 here as the weight of the leg. And its center of mass is 35 centimeters. So the distance from here to the center of mass is 35 centimeters. And then from the hip joint, the cord holding the string is 78 centimeters. So from here to here, we've got 78 centimeters. Okay, that's what we have. And we're supposed to find, let this be T1, and let this be, so this is an upward force, let this be T2. Okay, we are supposed to find the value of M. How do we find the value of M? If this system is in equilibrium, meaning that the force T1 is going to be, the tension T1 is going to be equal to the tension T2. All right. Now again, if this system is in equilibrium, meaning that the center of mass here, as in the torque with reference to the center of mass, is going to be equal to the torque with reference to the tension 1. Okay. So to do that, we can say the net force on this foot from the hip joint is going to be equal to 0. So if we take taking torque about the hip joint, the hip joint will give us, we'll calculate, right? So we have got the hip joint starts from here to here. The perpendicular distance here we've been given as 35 centimeters. The force is, of course, the weight. Mind you, we work with SI units, so we're going to have to convert 35 centimeters to meters and 78 centimeters to meters. For now, we'll say this distance, which is 0.35 meters, multiplied by 15 multiplied by 9.8. Okay, I'm going to let that be equal to the torque about T1. So that will be 0.78, okay, multiplied by T1, since that is a force. So to find T1, I'm simply going to multiply this. And if you multiply this, you're going to get 51.45. Okay, that is equals to T1 divided by 0.78 divided by 0.78. So T1 generally will give us 65.96 newtons. Okay, that's T1, which is here. Now, if you look at this, if this system is in equilibrium, meaning T1 is equal to T2. Okay? T1 is equal to T2. And if T2 is equal to T1, meaning now we are going to look at this system, this part of the system. So we'll have T1 is equal to T2, which is equal to 65.96 newtons. Okay, that's what we have. So now, if we have a system here, which is also, this part of the system is also in equilibrium, and if it is not moving, meaning that T2 is equal to mg, okay, the weight of this block. So we'll have T2 being equal to mg. Okay, so we'll have 65.96 is equal to 9.8 m divided by 9.8 divided by 9.8. So m is going to be equal to 6. So that will be 6.7 kgs. We can approximate that to 7 kg. Okay, so that's how you solve these questions. So today we've solved question 5, 6, and 7. We'll be doing question 8, 9, and 10 in the next video. Okay, that's all. All the best. Thank you.